All right, in this podcast, we're going to talk about chemical reactions. Make sure you have your handout or your podcast sheet ready. We're going to go ahead and get started. So chemical reactions. Now, a car can have nice chrome, which is appealing to a lot of customers. Over time, though, the chrome can rust. Now, that rusting is caused by a chemical reaction. And a chemical reaction is a process by which atoms or a group of atoms are reorganized into different substances. Chemical bonds are broken and formed during chemical reactions. Rust is an example of a chemical reaction. The oxygen is reacting with iron to form rust. Now, there are several clues that can hint that a chemical reaction has taken place. Sometimes there is heat or light in addition to a new solid, liquid, or gas being formed. This rust that forms is a new solid. It didn't exist with iron or oxygen. It is a chemical reaction of iron and oxygen that create rust. Now, substances can also undergo just a physical change. It's not rearranging the atoms. The atoms are not rearranged and no chemical reaction is taking place. The physicality of the object itself is changing. Now, an example of a physical change would be water going from a liquid state to a freezing state. When you have water in liquid state, it's H2O. When it's ice and it's frozen and it's in a frozen state, it's still H2O. There's no rearranging of the atoms there. It's just undergoing a physical change. Now, chemical equations. In written chemical equations, chemical formulas describe the original or starting substances on the left side of an arrow. And these are known as reactants. They are reacting to form new products. And that brings us to our next word. The products, which are the substances being formed from the reactants, they're on the right side of the arrow. Now, the arrow doesn't mean equals. If it meant equals, they would use a equal sign. They don't. So the arrow means yields or reacts to form. And here's an example of a chemical equation. We're going to take a look at reactants and products. Now, remember, reactants on the left side of the arrow. This arrow right here. Products are on the right side. The reactants are reacting together to form brand new products. So here we have glucose and oxygen, my C6H12O6. When that reacts with oxygen to form carbon dioxide and water. If I look on the left side, carbon dioxide doesn't exist here. I have sugar and oxygen. Over here, we have rearranged the atoms where carbon dioxide does exist. H2O does exist now, even though it didn't over here. All right, so balanced equations. You must balance a chemical equation. In chemical reactions, matter cannot be created or destroyed. You can't just get rid of atoms because you want to or you don't like balancing chemical equations. They have to be balanced, and here's why. This is known as the law of conservation of mass and sometimes called the law of conservation of matter. Matter cannot be created or destroyed. Now, in a balanced chemical equation, the amount of atoms of a particular element on the reactant side must be equal to the atoms of that same particular element on the other side. All right, now coefficients, which are large numbers in front of the element symbol, can be used to make the atoms on each side of the chemical equation equal. So let's take a look at that. In our last example, we didn't have a balanced chemical equation. Here we don't have one either. We have iron and oxygen, which forms rust. So we have 2 molecules of iron, 3 molecules of oxygen. Over here, we don't have the same thing, so we have to balance it out. In order to balance it out, we can use coefficients, and I said those large numbers, and that's what I'm talking about. Not these small numbers here that are subscripts, but these coefficients, which are the larger numbers. So I've balanced my chemical equation out. Here, I have 4 molecules of iron, 1, 2, 3, 4. Over here, I have 6 molecules of oxygen. But you might be saying, well, you have a large 3 there, that's not 6. Well, I have 3 molecules of O2. 1, 2, 3. I can also say 3 times 2 is 6. 1, 2, 3, 4, 5, 6. I have to balance it on this side because if I have this right here, it is not equal to this. I have to put a coefficient on this side as well. By putting a 2 here, I can get 4 molecules of iron because 2 times 2 is 4. I have the same amount. And then 2 times 3 is 6. It is balanced. I have the same amount of molecules over here as I do over here. They are in equal amounts. That is a balanced chemical equation. You don't get to think about whether or not you want to do it. You have to do it. It is required. And that is because matter cannot be created or destroyed. So let's talk some more about chemical reactions. Now, the key to starting any chemical reaction, it's all about energy. Now think about cookies. Here's an analogy anybody can understand. Even if you're not a science expert, you take some flour, water, sugar, you take some other ingredients. You mix them together, they don't turn into a cookie magically. You need energy. Now, in this instance of making cookies, the energy comes in the form of heat. You turn on your oven, you put the mix in, and the chemical reaction takes place, and it turns into a cookie. Now, in order for reactants to turn into products, there has to be a minimum amount of energy, and we call this minimum amount of energy that is needed activation energy. Now, your paper in front of you should burst into flames right now. At this moment, your paper should just burst into flames. Good thing it's not, that way you can keep your eyebrows grown in. However, the amount of activation energy needed for your paper to burst into flames is too high. You can lower it by using a match, and then the paper will burn. The same thing with a candle. Your candle's not just going to magically light. The match will light the candle, and then no more energy, this activation energy, is needed for the candle to continue to burn. Now, we talked about a candle. So we take a look at these reactants, which are on the left side of the arrow, and they form brand new products. The activation energy is what is needed. So the candle will not light by itself. It needs the activation energy, and that is done by a match. So the match provides the activation energy that is needed for the reactants to react and then to form a brand new product. So let's talk some more about activation energy. Now, because activation energy is needed, this could cause reactions to be too slow. I mean, you have to wait a long time. Well, CO2, that's toxic to you. It can kill you, and it needs to be removed from your body, and it can't be done slowly. If it's done slowly, you will die. So additional substances are present in organisms that lower the activation energy needed. And we call these substances, we call them catalysts. It lowers the activation energy needed to start a chemical reaction. Because it lowers the activation energy, chemical reactions can happen faster. Now, biological catalysts are called enzymes. So when we're talking about catalysts, we're talking about enzymes. And enzymes are special types of proteins. Enzymes are essential to many chemical reactions and are therefore essential to life. So if we're talking about catalysts, we are talking mostly about enzymes in the biological sense. Now, enzymes don't get used up. Once they start a chemical reaction and they form products, the enzyme can be used again. So here we have a catalyst happening, or an enzyme. And what's happening here is this is the amount of activation that we needed. With a catalyst, we see the activation energy doesn't need to be as much. It can happen much faster, because rather than waiting for the activation energy to get way up here, we can have an enzyme and it only needs to be right here. So it can happen a lot faster because the energy doesn't need to be as high. Happens much, much quicker. Now, enzyme names. So enzymes are named based off what they deal with. Now, we don't call them enzymes. There are special names of enzymes based on what they deal with. For example, amylase is an enzyme found in saliva. This is when food begins to break down, when it enters your mouth. When you put food in your mouth, it begins to break down. You don't have to wait. Amylase is an enzyme that begins breaking down food, and that amylase is found in saliva. Now, amylase breaks down amylose, which is a component of starch. Now, in the human digestive system, there are the enzymes lipase and protease. Lipase breaks down lipids, which are fats. So we see that's why it's called lipase, because it breaks down lipids, which are fats. Protease breaks down proteins, which is why they have similar starting words. And most enzymes are specific to one type of reaction. For example, protease are going to break down proteins. They're not going to work to break down lipids. So most enzymes only deal with one type of reaction. Now, speaking of enzymes, you may have also seen an enzyme substrate complex and products. And we're going to talk about that right now. And all it is the stage of the enzyme substrate, where it is and what's going on. Very easy to understand, not too difficult at all. So don't be overwhelmed by these words or even intimidated by these words. Now, reactants that bind to enzymes are called substrates. So remember, the reactants are on the left side of the chemical equation. They react to form products. When they bind to the enzymes, we don't call them reactants, we call them substrates. So really, reactants and substrates are the same thing. It's just when the reactants are binded to the enzyme, they change their name to substrates. Where they bind to the enzyme is called the active site. So we have an active site, and that's where they bind. And we're going to take a look at an image in a minute to clear this up. Now, the substrate, which is really just the reactants, and the enzyme, the active site, they fit together perfectly like a lock and a key or puzzle pieces. They have to fit together perfectly, and they do. Now, once the substrate binds to the enzyme, we don't call it an enzyme anymore. We call it an enzyme-substrate complex. Well, why do we call it an enzyme-substrate complex? Well, the substrate has become bound to the enzyme. Enzyme-substrate complex. All this means is that the substrate has bound to the enzyme. That's it. That's all it means. All right, the substrate has been bound to the enzyme. There's nothing fancy going on here. The reactants have bound to the enzymes, and we call them substrates. Very, very easy. Don't overcomplicate it. Now, the enzyme-substrate complex breaks down chemical bonds, allowing products to be released made from the substances. Now, the enzyme will release the products and then get ready to be used again. And remember, enzymes don't get used up. They get to be used again. And this is essential for biological processes and organisms. And the only reason your body can get rid of CO2, because earlier we said it's toxic and can kill you. And the only reason you're still alive and your body can get rid of CO2 very quickly is because of enzymes themselves. Now, when you're in biology class, you may see a picture like this, and we'll show you another one in a minute. So here we have these reactants. And we call them substrates because they're binding to the enzyme. Right here, where they bind to the enzyme, that is the active site. So right here, we have an enzyme-substrate complex. All that means is that these substrates are now bound to the enzyme. Right here along the active site, right here where they connect. And the whole point of them doing that is, say we need to use this green molecule right here. All right, whatever the substrate may be. Well, we can't get it when it's in this entire substrate. So a reaction takes place, and now we can break off this green little circle here, allow it to attach to this product that we can now use. That is the whole point of enzymes and the enzyme substrate complex. It's going to allow products to use. There's also another picture, and I like this next picture a lot better. So here we have a substrate. Here's our active site, right, where it's going to bind to the enzyme. And we need to use this, half circle here or whatever, and this triangle. That's what we need. But when they're in this, when they're chemically bonded together, we can't. So it fits together perfectly like a lock and a key. We have our enzyme substrate complex. The substrate has become bound to the enzyme. And then what's going to happen is it's going to break the bond between these two shapes, and you're going to be able to, your body's going to be able to use them because we are breaking the bond between them, and now we have the products to use. Nothing too complex there. If you have any questions, feel free to leave a comment below, and we'll see you guys in class.